Welcome back to a new lecture of engineering mechanics, and in today's lecture 18 we will focus on orthogonal hinged frames. And that means that we have to first talk about rectangular corners, because that is specific to our kind of frames today, because something very special is happening with them. And we will not just focus only on rectangular corners, because that is probably one easy thing that we can focus on, and so we can kill two birds with one stone. We also introduce hinges in frames in this case. We have dealt with hinges before, and so now we also implement hinges in frames. And our ultimate goal is, as actually always in this section of this class, to talk about the internal force diagrams and how those are created, in this case particularly for rectangular frames. So let's first understand what internal forces do when they interact with a rectangular corner. And to talk about that, let's first draw a frame. So I'm going to draw a regular frame here on my canvas, and I'm of course exaggerating a little bit. And keep in mind that we always had horizontal members before. Now we are dealing with horizontal and vertical members. So we are familiar with the reference fiber, and now completely randomly, or for no good or better reason or worse reason, I will put the reference fiber on the inner side of the frame. But nobody would stop me from doing that on the outer side of the frame. This is just by choice. However, this reference fiber that I just included defines where the positive and negative side of the frame is, as we will see in a second, or as we have seen before actually for our regular beams. And now, as always, I will release the internal forces at that location by cutting the frame. And to do that, I'm going to eliminate some parts here. And I can do the same thing on the vertical components, just so that I can release my internal forces. So the first thing I'm going to do is I'm going to cut the system. And I do that everywhere. Cut, cut. And to make my life easier, I'm also going to name these members. So I'm going to call this member 1, member 2, member 3, and member 4. I don't bother about the ones on the bottom. Those are not relevant for us right now. However, I'm going to use them to tell the entire story. So the first and easiest thing to do is probably to focus on member 2 and 3. And in member 2, I have a right side cut, so I can just use my regular study card that we developed in a lecture before, in which I bring in my internal forces, and those internal forces are the moment, the shear force, and the normal force. And as before, the shear force has to go down, the normal force has to go to the right, and the moment has to turn counterclockwise. And this is on account of the reference fiber being on the bottom here. So now same logic applies to the left cut in member number 3. So I'm going to bring in my internal forces here. But be careful now, because it's a left cut. Therefore, my forces are actually opposite to each other. Otherwise, they could not balance what happens in member number 2. So actually member 2 and 3 are one member, but I cut them in half. And they have to balance, of course, at that cut. Otherwise, the system could not be in equilibrium. So now for the first time, we're actually dealing with vertical members here, member 1 and member 2. And again, the reference fiber tells us what to do next. So keep in mind that the reference fiber pretty much tells us the direction of the positive and negative y-axis, but also tells us where x is positive. So for example, if I look at member 2 here, the x-axis is positive to the right, and then the y-axis would be positive upwards. The same is true if I shift my logic by 90 degrees here for member number 1. So the axis of the member actually becomes a vertical direction, and positive and negative y direction is to the left and to the right of this member. So let us introduce our internal forces at that cut now. So it's a left cut in this case, so my moment is clockwise. My shear force has to go up, which in this case is actually to the left, and my normal force has to go down. Which, of course, normal force, once again, is normal to the cross-section of the member actually, so it's in line with the axis of the member, and therefore it's going down in this case. Now, if I look at the bottom part of that, of course it's opposite because it's a right cut. So I would have a moment here, I would have a shear force here, and I would have a normal force that's going up. But we're not caring about these members right now, or about those components right now. On the other side, for member number 4, it's a similar story, but I have to use my study card again with those internal forces. So I'm gonna bring in my internal forces like that, the moment being counterclockwise, the shear force pointing to the left in this case, or down relative to the reference fiber, and the normal force going down or in line with the reference fiber but away from the cut. And now we see something very specific here because we're dealing with right-angled corners. So this is very specific, and we can memorize, or we can understand that the shear force, for example, acts relative to the normal force. So the normal force here, this normal force, is turning into the shear force at the 90-degree corner. So whatever force the normal force takes up here has to be balanced by the shear force in the corner. And I want to point out again, this corner can be like as tiny as like a millimeter only here, and this picture would still be true. And in that case, this force, the normal force, has to balance the shear force at that corner. But this is only true because we're dealing with a 90-degree corner. And I can do the very same thing with my normal force here. My normal force has to balance my shear force here. Or not balance, but they have to interact with each other, if you will. And the very same thing is, of course, true again on the other side. So maybe I can do a better job showing it this time. So the shear force here has to go and interact with the normal force. And the shear force at member 4 has to interact with the normal force at member 3. So that is something we can memorize, that at 90-degree corners, the shear force and the shear force and the normal force interact with each other, right? So at 90-degree corners, V turns into N, and N turns into V. Careful, however, because the moment does not change at the corner, right? Because the moment only turns about a point, and it doesn't matter if it turns, clockwise or counterclockwise, the value has to stay the same. And by the way, the same is also true for the shear force and normal force. Like the positive and negative is only defined by the reference fiber. So if the reference fiber here, for example, would be on the other side, then the sign of course changes, but physically it's still true that whatever is acting vertical in this member is acting perpendicular to this member. And so the shear force and the normal force in right-angled corners have to counteract each other and balance each other. Whereas the moment turns about a point, so you can think of it as this moment turning about this point, and this moment turns about that point. So the value stays the same at the corner, but you will see that when we actually run a real problem. So for now, it's important that we understand that the shear force and the normal force actually interact with each other in a particular case of a 90-degree corner. This is very unique to a 90-degree angled system. And so that concludes our 4.9.1 internal forces at rectangular corners. So we are almost ready to solve a problem, but remember that we also want to talk about hinges so that we can actually tackle two problems at once. So let's talk about hinges in frames. So what you will see from here on are problems that look like the following. For example, so I have two vertical members and one horizontal member, which is split by a hinge, and that hinge is right there. And now I need four support reactions, because if, for example, this was a roller, so if this support here, what I call A, would be a roller, this hinge would pretty much allow the system to slide out left and right. And so this would be a kinematic system and we could not solve anything. Therefore, I have to erase my roller support here and turn it into a pin. And that looks strange on the first glimpse for us because we have 1, 2, 3, 4 support reactions. And that is difficult for us to solve usually. So let's say I call this here RAY and this here RAX, then RBY and RBX. And so I have four support reactions, which is completely counterintuitive compared to what we have dealt with before. But it is absolutely necessary in this case because of our hinge here at the top. Otherwise, the system would just slide out. And so this is the minimum support reactions we need to create stability in this frame. Of course, in real life, you always will find that there's some load on the system. So let's just call this here F1. But the question now for us would be, how do we solve this? And of course, as every problem we dealt with before, if we want to talk about the internal forces, we need to find the external forces first. And the external forces in this case are the support reaction. In fact, that's what we're talking about here to begin with. So the support reactions. The question is, how do we calculate those support reactions? And the easiest way to do so is to set up two equations with the two same unknowns. So let me elaborate on that. For example, let's say I want to find RBY and RBX. Then I could pretty much have a subsystem that passes through the hinge, because remember that M at the hinge is equal to 0. And so I can create a cut that I'm going to call cut 1, if you will, in which RBY and RBX exist. And now I need to create a second cut in which the same two unknowns are represented. Before I show you that, let me show you a very common mistake that students tend to make. And that is, okay, if I can cut through the hinge, all I have to do is cut through the hinge again. And then set up my equations for this. Let's call this here cut 2, or actually let me call that cut 3, because I want to show you the right cut 2 in a second. But if I were to set up the equation for cut 1 now, which is this purple one here, and for cut 3, I would end up with two equations but four unknowns. So this is not helpful to us at all. Therefore, I need to set up another set of equations in which I have the same unknowns. And if I stick with my RBX and RBY, and I'm going to use the purple color to show this again, I just cut through this hinge and include the entire system here, everywhere around. And I'm going to call that cut 2. then I can set up two equations, right? So keep in mind the sum of the moments about any point is always equal to 0, counterclockwise positive. And so I can do that for cut 1 and I can do that for cut 2. So I also would have a second equation for cut 2. And of course, here in this example, we have no dimensions and no force really. You would have to include in the first cut only RBY times its vertical lever arm, which would be this distance. And then, sorry, RBX. RBX has the vertical lever arm of this system because it turns about that point. And RBY has the lever arm of this distance because that is the distance, the shortest distance between the hinge and the line of action of RBY. And so RBY would have this lever arm, RBX would have that lever arm, and that would be my equation 1. And now in equation 2, see that would take the sum of the moments about this point here, effectively about A. We would take RBX times the distance from here to here in a vertical distance. You will see that in a example that we will solve in a second. So again, RBY has a line of action that passes through here, and so that distance would be relevant. And for RBY, sorry, I might have said RBY here before, so I meant RBX. RBX has the vertical distance and RBY has a horizontal distance. So effectively from here to here would be the distance for RBY. But ultimately, in all of these problems in hinged frames, you want to solve a system of equations, two equations with two unknowns, in which you set up the same two unknowns in your system. So like I said, a very common mistake is that students try to, set up this cut 1 and then this cut 2 and then they want to solve it. But what those students did not account for is that then they end up with two equations with four unknowns, and that's unsolvable. Alternatively, however, you could set up a second equation that goes along with this cut here. So let me do that real quick for you. So you can also set up another cut which goes through the support at B. And so I could pretty much include everything here. And I guess I can call that cut 4. And so if I now use the sum of the moments is equal to 0 for cut 3, and then use the sum of the moments is equal to 0 for cut 4, then I can solve for RAX and RAY simultaneously. But I cannot mix the two. So the easiest way is always to think of these support reactions as two equations with two unknowns. And I need to find, of course, the two equations that use the same two unknowns. So in this case, it would be either the purple or the green component. And that concludes the support reactions for hinged frames. So now we're ready to solve a problem like this, where we have to draw the internal force diagrams for the frame. Let's take a look at the frame. What's obvious to us is that we have a concentrated moment here of 200 kilonewton meter. We have an evenly distributed force of 40 kilonewton per meter and an evenly distributed force of 20 kilonewton per meter. The system itself is interesting simply because support B here on the right side is higher situated than support A. And so that means that we have to deal with what we talked about before, that we have to set up our two equations with two unknowns. We also have a hinge here at x equals to 2 meter in a global system. But again, let me remind you that this dashed fiber here, the reference fiber, is actually a local coordinate system. So the first thing I should do is give myself like an identity that I probably call this here member 1. And maybe I even call this here 2, like where the force is not acting. And then I have 3, 4, 5, and 6. So I can deal with those. Then the next thing would be to draw my free body diagram. So let's do that real quick. So for my free body diagram, I have to include my forces. And this does not have to be 2-dimensional, but it has to be true to the general concept of the frame. So here's my hinge. And now I need to bring in my forces. So you see, drawing a free body diagram for a hinge frame is no different than it is for a beam. And of course, I cannot forget my concentrated moment. And now we can define our support reaction. So I'm going to call this here RAY. I'm going to call this RAX. And it's my convention to always put the forces inside to the frame. And sorry, I confused RAX and RAY here, so let me fix that. Sorry, RBX and RBY. And those are global, right? The X and Y, but we have to deal with the other parts now. However, what's important for us to understand is that we can either solve for these two simultaneously or for these two simultaneously. In this case, I would argue that it's easier to solve for RBX and RBY first, because if I make my cut through the hinge, I only have to worry about one force here, whereas if I do it on the other side, I have to include two, but it's neither wrong nor right to do it the other way around. So let us solve the system, and I probably should give myself a little hint here. This was 40 kilonewton per meter. This was 200 kilonewton meter, and then we have 20 kilonewton per meter. So instead of solving it on the bottom, I'm just going to solve it on the right, because then I can see all my dimensions properly. So I'm going to start with RBX and RBY. RBX and RBY. And the way I do that is by setting up two equations with the same unknowns. So first, I'm going to set up the first cut, in which I take the sum of the moments about the hinge. So I set up the sum of the moments about the hinge is equal to 0, counterclockwise positive, and now I can get started. So 0 is equal to, and I need to be true to my directions here. I cannot mess that up. I have to go with what I defined here for now, because I'm going to use these signs like here upwards and here to the left in both equations, and I have to be true to those. So I'm going to start with, let's say, RBX, and RBX is turning counterclockwise, if I'm not mistaken. Sorry, clockwise. I define it as clockwise about this point, and it's actually acting here. So that gives me a lever arm of 4.5 meters. So RBX times 4.5 meters. And that turns, like I said, counterclockwise. So therefore, sorry, it's clockwise, therefore it's negative. And now I'm going to deal with RBY. And RBY is really acting here upwards. So it has a lever arm of this distance, which happens to be 2.75. So times 2.75 meters. And that is turning counterclockwise this time. So this is positive. And now I need to include my 200 kilonewton meters here. So that turns clockwise, therefore it's negative 200 kilonewton meter. and I have the first equation for my first cut, which is effectively right through the hinge and everything here included. And so what will I do next now? I will actually take the sum of the moments about this point here, pretty much about the support A, and include all of it in my equation. So let's set up the second equation. So I'm going to call that the sum of the moments about A being equal to 0, counterclockwise positive. And now 0 is equal to, and I'll start with my same unknowns, R, B, X. Now it's important to be careful. So it's acting here and it's turning about this hinge. So effectively it's turning this way around, which makes it counterclockwise, so that makes it positive, but I also have to find that distance from here to here, effectively, from here to here in a vertical manner. So that would be a distance of 2 meters. So 2 meters. And now it's turning counterclockwise, as I said, so that's positive. Now I need to deal with RBY. And RBY is really acting upwards, so it's the distance from here to here in a horizontal fashion. So that would be the entire length down here. So that would be 4.75. So times 4.75. But now I have to decide in which direction this is turning, and it's turning counterclockwise, if I'm not mistaken. Yes, so therefore it's positive. And I want to re-emphasize this, right? So here it's plus plus, whereas here is plus minus. That seems strange on the first glimpse, but keep in mind that because you turn about this point in the first cut, and in the second cut you turn about this point, therefore this RBX takes a different rotation, right? It turns clockwise versus counterclockwise on one of them. All right, let's continue because I still have to include my distributed forces here and my concentrated moment. Let's start with the concentrated moment. That is still turning clockwise, therefore it's still negative 200 kilonewton meter. Now let's do the 40 on the top. So 40 kilonewton per meter, and that is acting over a distance of 2 meters, right? From here to here is 2 meters. And then I also turn about this point, so actually I have a lever arm of 1. So times 2 meters multiplied by 1 meter. Now I have to decide, is it clockwise or counterclockwise? And again, this force here is rotating this way around about point A. So therefore it's clockwise, and therefore that is negative. Last but not least, let's do the 20. So the 20 kilonewton per meter multiplied by 3.5 meters. And now it's actually acting directly from here to here. So it's 3.5 over 2 is the lever arm because it's an even distributed force. So that does not make that difficult. So times 3.5 meters, but divided by 2. And now we have two equations with the very same two unknowns. And that will make our life very easy to solve this now. I could have set up the same equations for the other side. In fact, for educational reasons, let's do that right now. Instead of solving these right now, I'm just going to set up the equations for the other side. So let me do that, and maybe I can do it on the same page here. So now I'm going to set up the equation for RAY and RAX. And I'm going to start with the sum of the moments about the hinge is equal to 0, counterclockwise positive. And 0 would be equal to RAX times, I need to be careful, is the height of that leg of the frame, which is effectively the distance from here to here. So that's 3 plus 2 plus, so 6.5. So times 6.5 meters. And it's turning clockwise, counterclockwise, so therefore it's positive. Next, RAY. And RAY is acting upwards. So it's this distance here, which is 2 meters. So I multiply that by 2 meters. And now I have to wonder if it's clockwise or counterclockwise. And it is pushing up, so it rotates clockwise. Therefore, it is negative. But now be careful, because I have to include my two linear distributed forces here, so the 20 kilonewton and 40 kilonewton per meter. So let's start with the 20 kilonewton per meter, which is acting over a length of 3.5 meters. But now be careful, because the lever arm now is about the hinge. So we're rotating about the hinge. And that means that now I have to pretty much take the distance from here to here, which would be 3 plus 3.5 divided by 2. And that's how I'm going to write it down. So multiplied by 3 plus 3.5 divided by 2. And that also would be in meters. But I'm not done yet. I have to include the 40 kilonewton. So let's do that. Maybe I can get that in the same line here. That is maybe not the best idea. So 40 kilonewton per meter multiplied by 2 meters. That's the distance it's acting over. And in this case, it's easy to see that the lever arm is 1 meter because it's right at the hinge. 1 meter. All I have to do is to decide a rotational sense, which in this case, it is actually going counterclockwise. We're rotating about this point. It's going down on the left of it, so it turns counterclockwise. That makes that positive. But by the way, we forgot the sign for this one here as well. Turns the same way around, so that is actually also counterclockwise. So they are both positive. And now I have that very first equation. Now I can set up my last equation, or my second equation for this cut. So the sum of the moments about B being equal to 0, counterclockwise positive, and 0 is equal to RAX. And what is RAX now? RAX is the distance from here to here. So that would be 2 meters. 2 meters, and it's turning counterclockwise. So therefore it's positive. So plus RAX times 2 meters. RAY has a lever arm of the entire distance from here to here in the horizontal direction. So that would be 4.75. So times 4.75 meters. And that would rotate clockwise, therefore it's negative. And now I have to include all the other ones. So I have my 20 kilonewton per meter times 3.5 meters. And now it's a little bit tricky. That can be really tricky, because the centroid here of this force is right in the middle, 3.5, right, to this point. So, but there's only a distance of 2. So let me actually draw that into the system. So the center of that load is acting here. And that would be 3.5 over 2, right? 3.5 over 2. And then technically here we also have 3.5 over 2. And 3.5 over 2 is not 2, as you know, some students sometimes tend to think here at this location. So that is actually So what we're really looking for is this lever arm. Let me introduce that. So we're really looking at this lever arm from here to here. And there's many ways of how you would define that, but effectively 3.5 divided by 2 is 1.5 plus 0.25, right? So 1.75. So effectively, we're looking at 1.75 here, and then here we have 0.25, if I'm not mistaken. So that means that our lever arm is actually 0.25. That is a little bit tricky, so that's why we're solving this problem here, but my lever arm is 0.25 meters. And it's below the support, so the resultant here is actually below this point, which means that we're rotating counterclockwise. So therefore this becomes positive. So this is positive. And now let's deal with the 40. So 40 kilonewton per meter multiplied by 2 meter. That did not change, but what changes is the lever arm, because now our lever arm is acting from the center of this to here, which means I have to account for all this distance here. So that would be 1.75 plus 1 plus 2 halves. So let's actually write it down that way. So 2 halves plus 1.75 plus 1, and that is in meters. And I have to decide for a sign now. So the force is rotating this way around, so counterclockwise, therefore it's positive. Last but not least, my 200, so plus 200, no, negative 200 because it's clockwise, so minus 200 kilonewton meters. And so you see we have two sets of equations that work now. So let me zoom out here and let me highlight for you which ones work. So I have this system of equations here in which we are solving for Rbx and Rby, and I would argue that this was the easier case for this scenario. Or we're going to use these two equations here in which we actually solved for Ray and Rax. And as you can see, those equations are a little bit more complicated, but it's not magical or anything more difficult to solve. Both of those will lead to results. However, we need numerical results for these support reactions to draw our internal forces. I recommend that you start to solve these equations with two unknowns just to get used to it and to be ready for the exam. I will just now provide the numerical values, and I would have found that Rax is actually equal to 64.16, but to the left. That's important. So my result would have been negative, but I don't use negative values in my drawing. So it's just 64.16 to the left, and Ray would have been equal to 2.28, and that is downwards. And so my answer would have still been negative in my two equations with two unknowns. But again, I don't use negative values here or negative values in drawings. So I just make that downwards. I could do the same thing for Rbx and Rby, which if I solve them, then I would find 5.84, and that would be positive, which means I assumed correctly to the left. And for Rby, it would be 82.28 upwards. So therefore, my result would also be positive in this equation or in the set of equations. And what that tells me now is that I have solved my support reactions, which I can use to draw my internal forces or internal force diagrams for this hinged frame, which is what we would do next. But this was the support reactions, and I think this concludes the ways of finding one side or the other. By the way, if I would have found only RBX and RBY, then I would have not had to go through all the lengths and solving these equations. I could have just used sum of the forces in X and sum of the forces in Y being equal to 0 to find these other answers. But this way it's a good check to see if I was right and if equilibrium works out. So one way or the other, you always want to check your results, and this is how I can do it here by doing the moment calculations first and then use sum of the force in X and sum of the force in Y for this to balance. And just to clarify on that, so we have RBX and RBY, so let's focus on the X direction first. RBX and RAX and also the 20 kilonewton meter, they all act in the horizontal direction, so they all together have to balance each other, which they do in our case. Similar, RAY, RBY, and the 40 downwards, they all act in the vertical direction, therefore they have to balance each other. And you can see that in our numbers, that is true, and so I can move on to draw my internal force diagrams now. So before I draw my internal force diagrams, it's always helpful for me to bring over my results. So I have RAY with 2.28. I have 64.16. And of course the direction is very important here. So that's 82.28. And I have 5.84. And now I can go ahead and use that information to draw my system or to draw my internal force diagrams. So let's agree that I will start with my normal force diagram here on the side, on the top left, and that is in kilonewton. And so now I have to look at the system and understand what is happening here. So if we remember correctly, there was the only force parallel to member 1 and 2. And let me remind you that this was member 1, member 2, if you will. And then we had 3 and 4 and so on. So I will actually erase those now to draw again, but those are my identities as I said them before. So in member 1 on the vertical left part, the only thing that acts in line of the member, the only thing that's acting here was the vertical force. And see that here we have 2.2 pulling downwards. That means that this entire member must be in tension. I don't even have to make a cut to do that. I mean, a beginner should always make a cut, but I can already see that there must be a normal force that is in tension, and tension is positive, and also it's constant. There's nothing else that pulls on that member. And now remember that we have the reference fiber here, and the reference fiber decides that this is the negative side and on the opposite side is the positive side. So tension is positive, that means I have to have a constant value here. And now you will see for the first time how to draw those diagrams. So you actually do that on a per local basis. So my member 1 and 2 actually look like this. So this is positive, and that would be positive 2.28. And this is the first diagram, or the first part of the diagram, the normal force diagram. The next easier one is the 82 on the right. So let's look at that one. So here again, the reference fiber is on the inside, which means the inside is negative, the outside is positive, and we have 82.28 clearly pushing on this member here. That means it's pushing up. So that means this is in compression, and compression is negative. So that means I have to at least start out here on the left side. But if we remember, there was no other force acting anywhere here on this, well, there's force acting here on the top, but there's nothing really going on here, and certainly nothing parallel to the axis of the beam. So therefore, I might as well draw a negative box there. And this becomes sometimes tricky for somebody who has never done this before. And I'm going to exaggerate that corner up there. So, because I want you to understand that the part for the vertical member has not anything to do with the horizontal member. Of course, they are connected to each other and the values are dependent on each other. But in terms of this corner here, that is like not related of what you draw for this part. So students often try to make sense out of this member and this member and this member together, but no, this is independent of this one for the sake of this diagram. So in fact, let's start to look at this. So now we need forces that push this to the side, or like that actually push along the axis of this member. And I guess the easier one to start with is using the force down here. If I were to make a cut here at the system up here, you can include all this and bring your internal forces here. But what you would find is that your normal force is only affected by the 5.84. And so that doesn't change anywhere to here, and it also doesn't change anywhere here, because remember, you only had a distributed force up here and nothing else. So the normal force diagram is almost done now. It's very easy to draw, and again, I'm going to exaggerate this. So I'm going to draw it up to here, and then I have to go back to 0 at the corner. So I'm going to go back to 0 there and back to 0 there. And this now is also negative because it's in compression, right? The 5.84 is pushing on that. And the 5.84 is minus 5.84. I also forgot to make this here negative 82.28. And now I'm effectively done with my normal force diagram. Of course, I will explain to you a few things real quick. So I say again that this 5.84 here has to close and go back to 0 at that corner, whereas the 82.28 here, of course, has to go also back to 0. So all this has to be closed. And you can always convince yourself by cutting here and calculating the normal forces. You can convince yourself cutting here and calculating the normal forces and so on. So what students often do is they want to somehow connect this point, like the horizontal to the vertical member. Please don't do that. Look at them individually, if you will. Or if you're in doubt, make a cut. Same thing here. They are independent of each other, if you will. Of course, we will see something related now when we talk about the shear force diagram, but for now, that is what we're looking at. One last word is students wonder, okay, here the 5.84 makes sense in context of this, but what about here? There's 64.16 here, and that is also horizontal. So how does that balance this? Yes, that is true, but don't forget that there was an evenly distributed force here. In fact, I'm going to draw that in here for you real quick. So there was an evenly distributed force here, I believe, of 20 kilonewton per meter. And so that cannot be forgotten, and that actually brings the 64, and this force actually back to a compression of 5.84. So that's what's going on here. It was just easier in my case to start here from the right side. And I believe that concludes our normal diagram. So now we can move on to the shear force diagram. Let's do that. And let me just use the color blue in kilonewton for the shear force. And now we have to start again. So I guess it's helpful to once again bring in my arrows. 64.16 and 2.28 and 82.28 and 5.84. And now I wish I could rotate this picture by 90 degrees, but it's virtual, so that doesn't really work. But I want you to imagine to actually look at this as being on the bottom, right? So remember what we've done in the past when we had like horizontal members. We always said, hey, if the reference fiber is on the bottom, we can start on the left side and then follow our arrows. So that works here as well, because effectively this arrow is under the reference fiber, and so I can just follow that arrow. And remember, there's the evenly distributed force here, so I'm going up, and then I'm going down, 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 and then nothing happens, nothing happens, nothing happens, and it goes back to 0. And the same is true here actually on the other side, except that now I'm on the right side. And so if the reference fiber is on the bottom, then this force here is on the right side of this cut. So if I look from the left to the right on this now, then of course I have to invert my logic. So I'm actually have to go against the arrows, but I will get there in a second. However, here it's true again, right? So I can start on the left side, and I can start with 2.28 down, because that's the only thing that's happening here. And then there's a distributed force here, which I probably should include as well. So let me remind you that there is actually 40 kilonewton per meter acting in this direction. And so we also have to think about that. But let's take it one by one. So first, I have to actually go up by plus 64.16. And then I have to, let's pretend that this is 1.5 meters above. So I'm going to pretend that this here is the line where the evenly distributed force ends. And so I have to go down from 64.16 over that distance with actually 20 kilonewton per meter. And so I will pass through 0 actually, and that will become interesting when we talk about the moment diagram. Let me just draw that properly for you. So here we go. And then I have the case where nothing happens, right? So nothing happens, nothing happens, nothing happens, nothing happens. And now similar to the normal diagram, it has to go back to 0 again. And again, I want to point this out to you that this part here actually belongs there, but I find it easier to communicate to students that it has to go back to 0 if I don't draw it on top of this black line. So that goes back to 0 there. And I have negative values here, positive values here. And what is my value down here really? It's effectively 64.16 minus 20 times that distance, which also happens to be negative 5.84. So this is negative 5.84. And that diagram was easy to draw. And again, I'm drawing this right now because I already did the cuts and so on. So if you're in doubt about this, feel free to make the cuts. It will always help you. But the reason I was able to draw this is because I just flipped this 90 degrees on its side, and then I followed my arrows. I went down, 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 down. Nothing happens, and then it has to go back to 0. So, and now it becomes interesting because we have to do the very same thing for the other direction. And I guess it's easier if I zoom in here. So I have to first go down now. So I'm going to focus on this horizontal member here, the entirety. Remember, there's an evenly distributed force here. So I am going to first follow my arrow, which is the support reaction on the bottom, which was negative 2.28. Or it will be negative 2.28. So let me draw that. So this here would be negative 2.28. And then I go down by 40 for every meter, right? So I go down, 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 down until I hit the hinge, because that's where the evenly distributed force ends. And if I go down with 40 over that distance, I end up as minus 87.28. Sorry, minus 82.28, right? Not 7. 82.28. And then again, nothing happens, nothing happens. Nothing happens, nothing happens, nothing happens. And then it has to jump back up, and I will explain that to you in just a second. So this jump here originates from this force, right? So this brings it back to 0. And so now I'm done with that part. All of this stuff here is negative, of course. So all this is negative. And now, last but not least, I have the part on the right side, the vertical part. And I make my life easy. Instead of starting from here, which I could do if I move my head or like my paper and rotate it by 90 degrees, then I can just, I could follow my arrows if I start on the left side, but I want to start on the right side. So I just go against my regular logic. So 5.84, the arrow goes down. So that means I have to go up on my diagram. So 5.84, that would be positive if I'm not mistaken. And then nothing happens again, right? So nothing happens, nothing happens, nothing happens, nothing happens. And then I have my diagram here, and this is all positive, and it is positive 5.84. And you see, I already drew my shear force diagram without running any numbers. Don't get me wrong, you can run numbers, and you probably should, but ultimately you should reach the point where you can use that logic to move your way around. So I want to emphasize, yes, here there's a hinge, and often, as I said before, when we talked about hinge beams, students want to think of the hinge as being 0, but that's only true for the moment, and we'll come to that when we talk about this diagram down here. But for now, there's a value here. In fact, it's the value 82.24, and then it starts sloping up. Last thing for me to do is to calculate pretty much this distance here, because remember that where the shear force goes through 0, my moment is maximum, and of course I want to calculate that. So I want to really understand this distance here. So let me zoom in there. And I have these distances. And you can find that in many ways, similar triangle or something like that. So x actually happens to be 3.208 meters. And so that leaves this here with 0.292 meters. And this is different for, like, the point of this lecture is not to show you how to calculate that. We talked about that in previous lectures, but it's either similar triangle, or you can set up the equation for this sloped line here and then set that equal to 0. All right. Now, last but not least, we have to focus on our moment, and let's, as always, do the obvious parts first. Moment in kilonewton meter, and we know that it must be 0 there. We know it must be 0 there. We know it must be 0 there. We also know that I have a parabolic function here, x squared. I also have x squared there. And then I have it linear. So that would be x and x, but don't be fooled. Remember that there was a concentrated moment somewhere here. So there I must have a jump. And then last but not least, here I must have a function of x. And by the way, here also I have x. But I will erase this now just to not confuse myself when I go through those drawings. But I know where it's linear and where it's not linear and where it's parabolic and so on and so forth. So it always helps to look at the shear force diagram at the same time. And let's start at the bottom part. So here we know we have a positive slope, positive slope, positive, negative slope. So that means that my parabolic function must go like this. So again, I started at 0. So it must go up, 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 and then go down at some point. So, and here where I have the maximum, that distance would be 3.208 meters. We'll come back to that in a second. What's next easy thing to know? So I know that it's 0 down here, and it must be linear on this one, and in fact it must have a slope of positive 5.84. So therefore I might as well draw a linear line, and that looks like this. And I'm going to zoom in to complete this. And what is the ultimate value at the corner? The value at the corner is effectively the support reaction, which is 5.84 multiplied by the length, which that length is 3.5, if I'm not mistaken. Or is it 4.5? It's 4.5. So 4.5 meters. Right? And so the value at that corner is actually negative, by the way. And so that is negative 26.29. All right, and we know that this is negative. And remember that at the corner it's constant, so I'm going to use a different color now just to emphasize this better. But this line here is actually also the very same value. And so now I have to be careful, because my first attempt or my first intention would be, hey, it has to go to 0, so it's easy to draw this. But that means you forgot about the concentrated moment. So let's erase that. So I have to actually go up first, and I have to go up with a slope of what I can read from my shear force diagram, 82.28. So that means that ultimately I will have to go, because it's 1 meter, right? I have to go up in that direction. Then there's the jump of my concentrated moment, and then it has to go to 0. There's no way around that. So this is a must. I used to jokingly say that if a student puts a value here in the moment diagram, that I have the right to fail the exam, but obviously I only subtract points. But please understand that if you do not put your moment diagram through 0 here, you did not understand the hinge, and you need to pay more attention to the details that we're trying to discuss in these lectures, right? So this is negative, this is positive, and then I guess I have to zoom in here. This is negative. All right, I can also calculate now the value at this corner. Well, so I have to calculate the value at this corner here, and of course my slope cannot change at the hinge, so effectively I have something that goes like this. And pay attention to your shear force diagram. Let me point you to it. So your shear force diagram does not go through 0 here. That means that I cannot reach a maximum here. Well, I mean, there will be a maximum relative to this, but there will be no change in slope, right? So I will have the maximum value right at the corner. So let's draw that. So it will look like this, and it will close here, and this is positive. And again, it's a 90-degree corner. Actually, it doesn't matter if it's 90 degree or not in this case when it's the moment, but of course the value here on both sides. So M M1 and M2 are equal to each other. And again, linear. I have to make a linear connection between those points, so let's do that. Technically, my drawing doesn't show it, but technically this tangent here actually is tangent to the curve at that point. But the last thing for us to do is calculate the maximum moment and the value here, because it's also the value here. And I guess we also need to calculate those values, which I believe we already did effectively, like I said. So from here, the slope up, so minus 26.28 plus that slope here. So let's get started on that. So we have a value of plus 55.99, and then we have negative 144, and in the corner we have 84.58, and that's positive. So here we have plus 84.58. And then last but not least, our maximum value here. And I just recommend that you go ahead and make a cut here and go through that exercise of calculating that. In fact, I'm going to do that real quick for you. So I'm going to calculate. I pretend I cut the system at that location. And I put my distributed force on there. And of course I have support reactions, which are actually 64.16 and 2.28. Although I don't need that 2.28, but I need you to understand that I just cut the system here. And I'm now calculating my moment there. And this distance here is 3.208 meters. So now I can calculate my moment by sum of the moments is equal to 0. And 0 is equal to minus m. No, it's plus m. Max plus 20 kilonewton per meter multiplied by 3.208 meters, and now multiplied by 3.208 divided by 2 meters. And of course I need to account for my support reaction, but that one is acting clockwise, so therefore it's negative. So minus 64.16 kilonewton multiplied by 3.208 meters. And if I solve all this, I actually will find the maximum moment, and the maximum moment actually happens to be positive 64.16, if I'm not mistaken. Sorry, that's not true, 102. So 102 is, so therefore M max is equal to 102 kilonewton meter. So what we now know is that this value here is 102. So 102 kilonewton meter. And that is an important value because that's the maximum value. You can now do the same thing at this location, and I recommend you do that because in an exam you also would have to provide that value over there. And in the same way, by the way, you can also calculate the value at the corner or everywhere, anywhere you want really. So it's always in the cut. But let's review this real quick. So now we have drawn for the first time the internal force diagrams for a rectangular frame, normal force, shear force, and moment. And as normal before, or sorry, that's a bad choice of words here, but as we did before, we used our same logic. So for example, for the normal force, tension and compression is important, and it defines our positive and negative values. If nothing changes, then it's just constant, and that's mostly the case for us in this class. And we were able to follow that logic here. For the shear force, same thing as before, except you have to get comfortable with the fact of like rotating your system by 90 degrees to follow your arrows. So here 64 up, down, 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 nothing happens, nothing happens, nothing happens, boom, back. And then the same here, except at this corner you have to kind of look down here and use that 2.28, because along this beam there's nothing else that's acting vertically. So only that goes down, and then it goes down by 40 per meter. Then nothing happens, and it goes back up. And last but not least, here on the right side, because the reference fiber is on the bottom, I just followed that logic and I inverted it, right? So instead of I started on the right side, and instead of following my arrow, I went against it. So I went 5.84 up, and then nothing happens, and then it has to go back to 0. And let's compare this, right? So the 5.84 here is reflected in the horizontal member for the normal force. 82.28 in the right member is reflected in the shear force for the horizontal member. So you see, whatever is vertical here carries over to the shear force in the top member. And the same is true here. 5.84 at this corner for the vertical member is reflected here in the horizontal member. 2.28 is reflected right here. And so that's a way you can check your logic there. Similarly, the moment diagram down here relates to the shear force diagram, just like we learned before, where the shear force is the derivative of the moment or vice versa. Just be careful when you follow your integration logic, right? Because also you could say that your moment is the integrated shear force. Be very careful when you go down that route, because you want to not forget about the integration constant here, which is the concentrated moment at that location. So with that said, I think we now understand how to calculate frames that have right corners and that have a hinge, right? So the hinge was the starting point that challenged us, because we now had to understand that we can solve the support reactions in a very specific way. But then after we found the support reaction, nothing new, nothing different than before. We just had to follow the logic and of course adapt it towards our sloped views, if you will. So that concludes this problem, and I believe we have solved for all the significant values and we have deciphered each part of the frame. So now I can go through my exercise here and kind of re-emphasize what I learned, what were my takeaways, and of course also what is still fuzzy to me. As always, I will not deal with that here in the online lecture. I leave that up to you. You should do that, however. What I will do with you is reiterate what we have done. So to me now it's clear that the internal forces for rectangular hinge frames can be determined just like I did it before. And I, of course, now completely buy into the idea that the shear force in a vertical member translates into the normal force at the frame corner into the horizontal member, and so on and so forth. So I can check that off too. The bending moment, of course, the bending moment remains constant at the corner, because opposite to the shear force and the normal force, the bending moment actually rotates about a point, and it doesn't matter if the point is on the vertical member or on the horizontal member, as long as they're like very much close to the corner. And if I put all of that together, I can also efficiently draw my diagrams for rectangular hinge frames. Don't be fooled. Of course, it takes practice and problem solving to really get familiar with that. but I believe we have really deciphered this, and you can now draw your diagrams. At least you know how to. Of course, practice makes perfect, and that's what the homework is for. So therefore, let's go ahead and move on, and let's take a look at the upcoming homework. To no surprise, our homework focuses on orthogonal frames. You see the first 4 out of 6 problems here on this page. So let's take a look at all of them. They all have a right-angled corner. Some of them even have 2 right-angled corners. But the first 3 problems are slightly different from the last 3, as you will see when we take a closer look. So let's take a look at the very first frame here, for which you're supposed to find the support reactions and then draw the internal force diagrams. Now, what you can see here is that it has a pin on the horizontal member and a roller under the vertical member. Now, for these frames, it is important that you identify where your reference fiber is. Of course, you have used the reference fiber before, but you didn't really need it. In this case, especially for the vertical member, you want to identify if it's on the right side or on the left side. I choose to always put it on the inside, but there's no right and wrong about this, so you could also put it on the other side. In fact, you may want to practice and see what happens if you put the reference fiber on the left side, because remember what the reference fiber does. The reference fiber is a local coordinate system. So for example, for this member, this reference fiber defines the coordinate system, and then for this member, this reference fiber defines the coordinate system. And it defines the positive x direction and the positive y direction. And so you can imagine that if I put the reference fiber on the other side, which you're very free to do for these vertical members, then the diagrams might look very different, or at least they appear to be different. Of course, physically, it doesn't change, right? Like, you cannot differentiate the system physically by drawing the fiber on the other side. Physically, everything has to be still true. So this is just a trick we use as engineers to have a better communication. But you need to communicate where the bending moment is positive and where the bending moment is negative, so that later on engineers actually know, for example, where to put the reinforcement steel and so on. You will learn this in later classes, but it is very important that you identify where the positive and where the negative direction is. So I suggest that for this frame, you just put it on the inside, and then I think everything else is as before. You don't need to solve the support reactions through 2 equations with 2 unknowns. In fact, the first one here you can find is the vertical support reaction at A. You just take the sum of the moments about this point, and then you have your vertical reaction. Then you can find the vertical reaction here, and there's in this case no horizontal reaction. And then please remember something I showed to you in this lecture, that the diagram for this vertical column is different or separate from the horizontal beam. So sometimes I see students who try to make a connection here from the diagram of the vertical member to the horizontal member, but you should really look at them separately, and I believe I have shown that to you throughout the lecture. So please pay attention to that. All right, let's go to problem number B, which is a very interesting frame, which is actually upside down, as some students sometimes call it. But in reality, it's just a horizontal member that has a vertical member welded to it. So this corner here is 100% stiff, and it needs to be connected rigidly. And the roller is just sitting underneath the horizontal beam. So think of this as a simply supported beam with a corner welded to it. And once again, you kind of want to identify where your reference fiber is. For this problem here, the way I would do it is just on the bottom, as I always do, and then I also choose the inside. You could have, for example, also moved this reference fiber to the top just for practice purposes, or you could put this to the outside, then it would pretty much line up with this one. It's up to you, but my personal convention is inside and bottom. That's how I usually do it. Notice that you have a force here, which is horizontal, that therefore causes a moment here of that corner. So you can really think of this part as a cantilever. This force also produces a horizontal reaction here. And I think if I tell you anything more, I solved the problem for you, and you clearly don't want me to do that, right? So let's take a look at the next problem, So now we have a frame with two right-angled corners or orthogonal corners. One is here on the left and one is on the right. But to find your support reactions, you really don't need to consider anything differently than you've done for beams in the past. The only thing that changes is how you find the internal forces in the vertical member. Once again, I probably would put my reference fiber on the inside so that I can unify my findings, but it is really up to you where you put it. However, the internal forces, they are slightly different than they were before in a beam, but I think the lecture provides you all the knowledge you need to solve this problem. Just understand that, again, this is an easy problem compared to the lecture that we've done or the example problem that we've done, because it's not a hinged frame. It's just a simply supported frame, as you can see here. So I have a roll light, not a pin and a pin. If I had a pin here, I needed a hinge somewhere. In fact, that is what we see in our next problem. So in problem D, we actually have a frame that has a hinge here at the corner and is loaded with an evenly distributed force from A to B and has a triangular distributed force on the vertical component. Notice that this problem is very similar but not identical to the problem that we saw in the example problem throughout this lecture, and that is these two supports are actually at the same elevation. In this case, elevation is kind of like in the x direction here, so they both have the same x value. Let's consider this here the origin of the coordinate system, so they both at x equal to 0 if we look at a global coordinate system. And so there's actually an easy way and a difficult way to find the support reaction for this one. So if you take the sum of the moments about this point, you can either take this part or you can take this part. And for one of those equations, either this one or this one, you will end up with one equation with one unknown. And for the other one, you would actually end up with two unknowns in it. And I'll let you figure out how that is and which support reaction to find first. There's an easy way and a hard way, so always work smarter, not harder. However, once you've done that, please identify where your reference fiber is. I always do it on the inside, so I suggest that you use this way. However, there's nothing wrong with doing it any other way as long as you're consistent with your answers. So please keep that in mind, that you always have to identify the reference fiber first before you can make sense of your internal force diagrams if you deal with more than just a horizontal member. Now that completes all the problems that are listed on this page, but we always have to solve 6 homework problems. So let's go to the next page to take a look at our remaining simply supported hinged orthogonal frames. So here we can see our last 2 problems for the current homework, and now it becomes really interesting because we now have truly hinged beams that have pin support at A and pin support at B. This symbolizes the hinge here. In this case, the system only has load on it on the left side. This is to make your life easier so that you can quickly identify your 2 equations with 2 unknowns to find your first support reaction and then move on. And then everything you learned from before in the homework applies as well. Once you found the support reactions, is really not different. So of course you need a reference fiber again, because that really determines how your diagrams are drawn in terms of positive and negative regions. So that completes this problem. Let's now move on to the last problem in the homework set, which is a very similar frame. In fact, for educational purpose, I made this very similar to the previous one, with the exception that now the system is loaded to the right of the hinge and to the left of the hinge. And this will make your equations a little bit more complicated, but this is on purpose so that you're better prepared for your exam, that you can identify how to fast set up your equations and what is the easy way and what is the difficult way. So this problem should really teach you where to start such a problem if you compare it to the problem on the other side. In fact, let's compare it to the problem on the other side. So this is done on purpose, that we have it actually mirrored the frame itself is mirrored over this vertical plane, but it's differently loaded. And in fact, pay attention to the load of this frame here, which has a horizontal force that passes through this support, whereas here there's a force that actually is removed from this support and this support. And in addition to this one is pushing on the frame and this one is pulling away from the frame. So please pay attention to that and see what effect it has on your final diagrams. Of course, once you reach this problem here, problem F, you're so far advanced with all your internal force diagrams that I don't really need to give you any more tips here or suggestions. I don't even need to tell you where to put the reference fiber and so on and so forth. So you will be a mechanics champion at this point when you solve these problems. But that completes now our homework. And I think this prepares you well for the upcoming task. We have one more subject to cover before we go into the exam. And that is, we will actually take it from orthogonal frames to non-orthogonal frames, or in other words, roof structures. So in our next lecture, we will not have a right angle in the frame. We will actually have sloped members. So not a horizontal adjacent to a vertical, we will have a horizontal adjacent to a sloped member, or just a sloped member to a sloped member, for example. And you will see that in a roof structure, but more details on that in our next lecture. Just come prepared, please. So this is really targeted to prepare you for that, so that we can really focus on the last issue that we need to cover during our next lecture. I hope that you will have fun studying this material, and I wish you good luck with that. I see you in the next lecture. Until then, stay safe.